winter talks for this year. And I would like to introduce once again Bob Holdsworth. He's kindly come back, so hopefully he enjoyed his last talk as much as we enjoyed it. Just as a reminder, Bob is a Professor of Structural Geology at Durham University. And my shorthand for his scientific career, he's an expert in the cracks in rocks, but he can tell you otherwise. Um, he's well known for the practical application of his science and has received over the years a lot of funding from industry, including the oil and gas industry in particular, and nuclear industries. Bob is a champion of public understanding and engagement with geology, and has, until I think fairly recently, chaired the Scottish Geology Trust. So, given the excellent talk he gave us last time and gave us a bit of a brain teaser, it will be interesting to see what he has to tell us about the geology of Foula and why it matters. Over to you, Bob.
Oh, thank you very much, Stephen. Well, hello, everybody. What I'm going to do, if you don't mind, is I'm going to actually turn off my camera because when I actually speak, I'm going to be standing up and you'll be seeing my big fat belly if I stand up. So I'm going to do that. If that's all right, I shall put it on again. I just need to share my screen now, which means I think, let's try that one. Let's just swap these displays over. Right, have you got the correct screen? Are you seeing the correct screen here, folks?
Not yet.
Not at the moment, no, Bob.
What are you seeing?
Just the normal everybody.
All right.
Gallery.
What about now?
That's starting to look better.
Right. Yeah.
It's saying you've started. Yep, we're seeing. Yep.
Right.
That's
Let
good.
me just where's the spotlight? No, that's not what I want. Oh, this will do for now. Okay.
Yep, that looks good.
That looks good. Great. Right. Just get rid of my chair. So, the geology of Foula, why it matters. Well, I feel a little bit of a charlatan giving this talk, to be honest with you, because I've actually only visited the island of Foula once. It was an extremely memorable visit, and here you can see me standing on top of the highest hill, on top of the big cairn there, and looking at the incredible view, including this view here. And it is one of the most remarkable places that I've ever been to, in all honesty. Right, but I need to give credit where it's due, because actually the people who've done all the hard work here are the two individuals shown at the top of the screen on the right-hand side there. Tom Utley, who is the young man holding the pie, one of the famous Lochinver pies, and Graham Blackburn, who's the older gentleman to the right. They are the two who did most of the work that I'm actually going to be presenting to you, including, I believe, in Graham's case, I think he actually spent his honeymoon on Foula, or at least part of his honeymoon there. Also Eddie Dempsey, Andy Morton, and Rob Strachan, who I know you've heard from on a number of occasions. I'd like to thank Jim Henderson, who may or may not be with us, for his logistical support in Shetland, and then various people on Shetland, including Callum Fraser, Jim and Richard Scott, and the crew of LK241, Magnus Holborn, and of course the residents of Foula itself. And also thanks to BP, who provided some of the imagery and some of the funding and support for this project related to the Clare Joint Venture Group. So, the island of Foula. Well, I'm assuming that you all know where it is. Here it is, highlighted in red, about 20 to 30 kilometres west of the mainland in Shetland. It is one of the most remote inhabited islands in the UK. It's about 13 square kilometres. It has a low-lying eastern side and rising up quite sharply to the west to these very, very high cliffs, which form the western side, the highest of all being Dakame, which get up to heights of over 360 metres. There are 5 significant peaks, the Schnurg being the biggest. Incidentally, if I murder some of these pronunciations, please accept my apologies. That picture that had me stood on the top of the cairn was taken there. And it's indeed over 400 metres high. It's a spectacular coastline. It's wild. It has many beautiful rock formations in terms of its geomorphology, including some natural arches, such as this one over here, which is the Garda Stack. It doesn't really have a proper harbour as such. It's only got one very unsheltered shingly beach up here in the north. And the main thing that you find when you spend any time on Foula is that it is always windy, and quite often terrifyingly windy. Foula, of course, is Old Norse, or it's derived from the Old Norse fugli, which means bird island, which is very appropriate as there are literally tens of thousands of birds living on the island. It's an island that's reached either somewhat irregularly by boat or more regularly, weather permitting, by an aircraft that's operated by the local council. Coming out of Tingwell. It's got one road, as you might have seen from the map in the previous slide, but many, many derelict cars, which are given over to a variety of things here for the growth of tomatoes, or at least I was assured it was tomatoes and not anything more sinister. It has a post office, it has a school, but no shop. There's something like 30 or more inhabitants, plus a lot of ponies, a lot of the beautiful Foula sheep, which are a unique breed to the island and which have absolutely no fear of heights as far as I can see. And of course, even more seabirds, including the totally terrifying, well, for me anyway, bonxies or great skewer. Famously, of course, Foula is supposed to be a place that follows the Julian calendar, so it doesn't celebrate Christmas at a different time to the rest of us. And it had its own language up until 1720, when 90% of the population was wiped out by smallpox. The language is largely gone now, though it lives on through the bird and place names on the island. Foula was the setting for the Michael Powell film made in 1937, The Edge of the World, which was a dramatisation loosely based on the evacuation of St Kilda. And it is, and I didn't know this at the time that I visited, the home of literary scholar and former professor of classics at Durham, my own university, Martin Ferguson Smith. I wish I'd known he was there because I would have gone and said hello to him had I known that. I'm told, or well, it is said in the deepest, darkest recesses of the internet that it's a place that isn't much visited by Shetlanders, but I'm not going to confirm or deny that. Right, let's talk about the geology now. Thinking about, first of all, the regional context, okay? Well, here's this kind of regional map, okay, showing northern Scotland, Orkney and Shetland up here, and there's Foula just nestling off to the west of Shetland. Now, in terms of the regional context of Shetland itself, as I'm sure you all know, Shetland and Orkney form part of a Caledonian metamorphic basement ridge, which is overlain by Devonian cover sequences. The basement shown in white offshore, grey onshore, and the Devonian shown in the orange colours, both onshore and offshore. And these older rocks are then flanked to the northwest and to the southeast by younger Permo-Triassic to Cretaceous rifts, Cenozoic sag basins, and of course, right out in the far west, we have the impinging tongue of the tertiary basalts sticking out towards, or coming from Iceland towards Shetland. On the map, what we're looking at basically here is a series of superimposed rift basins. You've got the older Orcadian basin, which is Devonian in age, which is then overlain, the Orcadian basin extending from the Moray Firth in the south right up through Orkney, Shetland, and on to western Norway. And then that's overlain by and partially flanked by a series of younger basins, the Moray Firth basin, the West Orkney basin, the West Faroe basin, the Unst basin, and so on, which are the Mesozoic basins. And then further out still, you have the Faroe Shetland basin off to the northwest, and of course the main North Sea basin off to the southeast. The ridge, the Shetland Ridge, is cut by a number of steeply dipping strike-slip faults, or mainly strike-slip faults, the Melby Fault, the Wolds Boundary Fault, and the Nestings Fault, which are traditionally viewed as being some sort of continuation of the Great Glen Fault in mainland Scotland. So Siluro-Devonian strike-slip faults, which have then been reactivated during the later Carboniferous and also the Cenozoic. The only other feature of note on the map to just highlight is the Clare oil field and the Clare Basin out here, which is actually buried underneath the Cenozoic cover sequences. It's a a quite small but separate Devonian basin, separate from the Orcadian basin and separated by this big basement ridge here. And that, of course, is the region that hosts the Clare oil field. And it's associated with another up-faulted basement high, the Rona Ridge here. So that's the Clare field in the cross-section there. And the main part of Shetland is over here. And there's the Rona Ridge there, Faroe-Shetland basin out here. But, okay, that's the sort of present day context. But what about the regional context in deep time? Now, I don't want to get too bogged down here. I just want to quickly take a zip through the sort of, if you like, the almost the global scale evolution of this part of the world in terms of its early history. We have, from the latest Precambrian onwards, the development of Iapetus and then the eventual dance of the paleocontinents and the closure of that ocean. Key things being that in the latest Precambrian, Shetland and the northern part of Britain was attached to Laurentia and was separated from Baltica and Gondwana and Avalonia by this major Iapetus Ocean and the Tornquist Ocean. As we move into the Ordovician, basically what happens is that Iapetus begins to close up and the Avalonia rifts away from Gondwana, closing Iapetus and opening up the Rheic Ocean behind it. But what we're progressively doing here is bringing the two halves of what will become the British Isles eventually together. Avalonia and Baltica also converge as the Tornquist Sea closes up, Baltica rotates. And then as we move into the early Silurian, essentially Baltica and Avalonia become proximal to Laurentia so that they're communicating geologically with one another. And these early events in the Ordovician and early Silurian are the early stages of the Caledonian orogeny and include things such as the Grampian orogeny, which was to do with the closure of, or the collision of island arcs, which I'm sure you've heard about from others. We then have the terminal and final closure of the Iapetus Ocean with the various players coming together, Laurentia, Baltica and Avalonia. We have a hard collision between the Northern Highlands and Shetland and Baltica during the Scandian event. We have a soft collision at much the same time between the rest of Scotland in Avalonia and in Laurentia and Avalonia to the south. And the development overlapping with that of major sinistral strike slip displacements, which will ultimately move the Northern Highlands and Shetland down towards the main part of Scotland. And those strike slip events began in the mid-Silurian and continue right into the middle part of the Devonian. So the Caledonian metamorphic rocks, basement rocks of Shetland, are deformed by those Scandian events. They're also deformed in the Grampian events, and they're also affected by these sinistral shear displacements along the major fault zones. And we see a transition from early sinistral transpression, moving into the Devonian, to sinistral transtension. That's oblique extension with sinistral displacements. And that is part of a bigger story. Okay, so we've got a lot of extension and sinistral strike slip occurring along the major faults in Shetland, in Scotland. And we also see this up to the northeast in Western Norway. And there's a linked process going on here involving this sinistral transtensional rifting, this opening of oblique basins, coinciding with the collapse of the pre-existing orogenic belt, the Caledonian orogenic belt. And it's important because this combination of sinistral strike slip and extension leads to some of the very unusual structural features that we typically associate with Devonian basin development, which happen to be very well displayed in Shetland and also to a certain extent on Foula. And they link what's happening in Scotland and Shetland to what was going on at this time during the Devonian, particularly in Western Norway. So there really is a geological connection between the two regions. There's another very important later period of fault reactivation, which follows on from the Devonian. So at the end of the Devonian, we have uplift and erosion, and we have east-west compressional inversion of the Orcadian basin, which is related to dextral displacements along the pre-existing strike-slip faults, the Waltz Boundary Fault, the Great Glen Fault. And this leads to east-west compression and reactivation of those faults. And in all probability, this is due to the closure of the Ural Sea, which lay to the east of what had been Baltica. driving Baltica outwards towards the west and compressing this area here. It has in many textbooks, it's called Hercynian or Variscan tectonics, but it isn't, to be quite honest. That's very unlikely. This is more related, I think, to the closure of the Ural Sea. It is not the far-field effect of the Variscan orogeny. Now, why am I mentioning these later dextral displacements? I'm mentioning them because when we come to try to reconstruct the Devonian basins, which of course predate these fault movements, we have to take out those dextral displacements and restore the various parts of Shetland and off-lying islands back to their original positions as they were at the end of the Devonian. Now, I know I'm pretty sure I'm right in saying that you had a talk from John Marshall. You're not very keen on the sinistral transtension story, I'm told, on the Old Red Sandstone in Shetland and beyond. Here's his stratigraphic scheme for the Old Red Sandstone of Scotland, stretching from Shetland here on the right, which is right up here, of course, in the far northeast, all the way down to the southern uplands down here in the south. And this is the main sort of configuration. I'm not going to go into a great amount of detail. What I will just highlight about this, and I've got no quibble, by the way, with this stratigraphy, is two things. The first is that everything from the Moray Firth northwards represents part of the Orcadian Basin. And that Orcadian Basin covered a really quite substantial region in the area below the Moray Firth, Orkney, up into Shetland, and probably upwards and continued onwards into Scandinavia. The whole stratigraphy in this part of the world is essentially hung off the correlation of a number of lacustrine deposits, or fish beds as they're known, because they contain some of the earliest fossil fish known, specifically the Achernaris fish bed and the Ede Flagstone Formation fish bed. You can see the blue line, which represents the latter, the red line, which represents the former. And those fish bed deposits, which represent lacustrine deposits, are basically used to hang the stratigraphy. And it appears to be a perfectly valid way to look at that stratigraphy. So I've got absolutely no quibbles with any of this. If we focus in a little bit more closely on Shetland, what we see there are basically, Shetland onshore and offshore areas. We basically, in the Devonian, or the Old Red Sandstone, see three sequences of different age ranges. The oldest rocks, which are Iphelian, lie to the west of the Melby Fault. This is the Melby Fault here. And they include the rocks on Foula, the rocks in Melby, and those that occur immediately in the offshore area. And these include, of course, significant areas of volcanics, Papastur, for example, and Ishanes as well up here in the northeast. We then have to the east of the Melby Fault, we've got Old Red Sandstone rocks that are mostly Juvetian in age, and a similar age to Carboniferous lying to the far northwest in the Clarefield. So we've basically got older rocks in the middle, flanked on either side in the Devonian by younger rocks of the Clarefield, younger rocks of the eastern and central part of the Shetland mainland. Now, another very important thing to mention is that the Old Red Sandstone in the Walls area, the Walls Formation here, sorry, Wales, I think it's actually is the proper pronunciation, adjacent to the Standstill granite, are metamorphosed and mineralized, and that's thought to be related to the granite. And the only other place where we see metamorphosed and mineralized rocks in the region is down here in Fair Isle. And this is important because it's thought to be a marker that allows us to restore or to work out what has happened during the dextral displacements along these faults in the Permo-Carboniferous. Specifically, that if we want to look at how the rocks were arranged back in the Devonian, we need to restore Fair Isle and everything attached to Fair Isle, which includes southeast Shetland. We need to move it 50 to 80 kilometers up to the north to put it adjacent to, well, the Wells Peninsula. Okay, so that's just an important thing to remember towards the end of the talk. Right, that's enough of the regional stuff. Let's talk about the Geology of Foula. Now, everything I'm going to tell you comes from this paper, which was published in 2023 in the GeoSoc of London. If you really want to torture yourselves, you can go and read it because it's open access, so it's free to download. So if you click on that link or copy that link, it'll take you straight to that paper. Right, so let's first of all just consider zooming in a little bit more, on towards Foula. Okay, here's the island of Foula here, Shetland here. Foula is associated with a northeast-southwest structural high, which is known as the Foula Ridge, with a certain amount of metamorphic basement outcropping at the seafloor and on the eastern side of the island. And it's a kind of similar sort of setting to the association between the Clare Basin and the Rona Ridge that lies off to the northwest. However, important difference is that all the basement out here below Clare and beyond in the Foula Shetland Basin is essentially part of the Caledonian Foreland and is Neo-Archean in age, while the basement associated with the Foula Ridge is probably much younger than that and almost certainly lies above the Moyne Thrust, as this cross-section shows. So although there's metamorphic basement ridge, it's very different in nature compared to the metamorphic basement that occurs further to the northwest. Sitting on top, as we shall see in a moment, of that metamorphic basement, we have about 1,600 meters of Middle Devonian clastics, which are either unconformably overlying or faulted against Precambrian basement on the eastern flank of the island. And overall, the rocks here lie within a much larger half-graben filled with Devonian strata, which crop out either side of the island of Foula and are then overlain by the younger West Fayal Basin, which is Permo-Triassic. So it's part of this asymmetric graben, and it lies on the western side of the Orcadian Basin outcrop. It's also the region onshore that lies closest to the Clare Field. So this is these are the Devonian rocks that are geographically nearest to those which occur and host the oil within the Clare oil field. Okay, so there's a Google Earth image of the island of Foula, showing the main locations. Here's a geology map taken from Tom Utley's thesis, which is also the one that's in the paper. Okay, what can we see? We can see that here's the basement. The basement here is shown in the greys and the pinks. Okay, separated mainly by a fault, but also by a sheared unconformity in the south. The fault, it's known as the Foula Fault. It's a steeply dipping north-south structure. Here's the Devonian sequence, okay, which, as you can see, is openly folded by a large north-northeast, south-southwest trending syncline, which we can see in this cross-section here. There's the Foula Fault faulting the contact. There's the unconformable contact. That syncline plunges shallowly to the south-southwest, and you can kind of see that when you look at Foula from the east, from the mainland of Shetland, okay, where you can see the various steps which correspond to the different geological units you're looking at here. You can see they're all dipping off towards the south, or in reality, the south-southwest, with the low-lying area in the foreground, if you like, representing the basement. Now, in terms of the sort of geology, that's the formations names, the various formation names, and so I'll just take you through it. We've got the Precambrian rocks at the bottom, and then we've got a variety of sedimentary units that make up the Devonian sequence. Very importantly here, this relatively narrow unit of siltstones and fine sandstones, this is the Blobbersburn Formation, which is thought to be lacustrine and thought to be the lateral equivalent of the Achenaris formation, the Achenaris fish bed. So it's an important time marker. But let's just go through some of that sequence, starting with the metamorphic basement. Here are some pictures of that basement. Okay, the rocks here are amphibolite facies, sammites, semi-peelites, mafics. They haven't been dated on Foula, but in terms of the sort of typical lithologies that we're looking at, pretty likely they're equivalent to the Yell Sound group, which are Neoproterozoic rocks, which have some sort of Caledonian overprint. They are cut by a quite large microgranite sheet and lots and lots and lots of microgranite sills, which are referred to as the Ruscar head microgranites. Again, these are not dated, but they certainly are pre-mid Devonian because there are clasts of these microgranites in the basal part of the Devonian sequence. And in all probability, it's some sort of Silurian early Devonian granitic body. There are multiple phases of brittle and ductile deformation in these rocks, and the rocks are strongly foliated as well. A little bit more detail on the basement geology, or in particular the basement structures. The foliation in the basement is generally dipping towards the southwest, And at the northern end of the island, you can actually see a gently southeast plunging synformal structure, which you can pick out from the stereonet. There's the beta axis plunging gently to the south. Excuse me, to the southwest. And also subparallel to mineral lineations that are developed within the foliation plains. Fractures, there are various fractures, but particularly there are north-south fractures. You can see this very dominant north-south trend in the fracture lineament, in the fracture lineaments that are seen from the aerial images of the island, which mostly correspond to steeply east-dipping normal faults that have some associated quartz epidote and iron copper sulfide mineralization, which predate the granites, because the fractures cut the granites, but they are barren. The other thing is that there are some rare abnormal oblique silicon lines on some of the north-south faults, and very occasionally you see evidence where you have a north-south trending fault for sinistral drag, suggesting that some of these north-south faults have sinistral displacements, whilst the northeast-southwest set appear to show dextral displacements. Okay, so that's the basement. Let's move on now to look at the cover sequences. And we'll start by looking at the two contacts. So this is now a view from the north of the island looking south. Okay, so east to the left, west to the right. Here's the basement area, very low lying, as you can see. Here is the contact, and here are the Devonian rocks to the west. The contact is mostly a fault, okay, which is called the Foula fault, but there is an unconformity exposed at the southern end. Let's go and look at that unconformity. Here's a more detailed map of that unconformable boundary. Okay, so this is the basement. This is the lowermost part of the Devonian sequence. It sits unconformably on top of the basement. There's basement here. Here are Devonian strata. Over on this side, there are some faults complicating the story. But if we zoom into this little picture here, we can actually see the contact. I'm running my pointer along the basement. So this is sheared basement just here. And then this is a basal conglomerate. And that basal conglomerate, as you can probably see from the way it's all the pebbles have been stretched out and smeared parallel to bedding, is quite strongly deformed and quite strongly sheared. And you can actually map out a series of Riedel and anti-Riedel shears, which overall are consistent with a top to the southwest sense of extensional shear along the boundary. So although this is an unconformable boundary, it's been modified by tectonism. It's been sheared by predominantly extensional displacements. So the other thing I should say about this area is it's pretty terrifying to visit. You can just about walk down to this part of the contact, but it's otherwise inaccessible, which is why the use of drone images like these ones are so useful. I'll say a bit more about that later. Let's go and look at the northern contact now. The northern contact is entirely faulted. Okay, so what we have at the northern end is we have metamorphic basement here with faulted and folded Devonian strata faulted against it. Here's the actual fault contact without any annotation on it. So that's the basement there. That's the Devonian rocks there. It's in detail really complicated. There's a series of little lenses of breccia, okay, which form a sort of mullion-like structure trapped beneath the faults. There are little bits of basal conglomerate that have got trapped below that fault. So presumably this fault has faulted out the original or most of the original unconformity, but there are just relics of that unconformity left along the contact. There are also all sorts of south to southwest plunging folds and a variety of scales developed. Some of them just fold the little areas of conglomerate. Other ones are rather bigger and fold the bedding in the adjacent Devonian strata. There are curviplanar faults in various orientations. But the important thing to note is that the folds of the bedding here, the folds of the foliation in the underlying basement, and folds you can actually measure in the field are all broadly north-south or north-northeast, south-southwest trending. They're all basically subparallel to one another. So moving away from all of that tectonic complexity up into the overlying Devonian sequence, as I've said, we've got about 1.6 kilometers of predominantly sandstone dominated sequences, but which are laid down mostly in fluvial alluvial environment with frequent flooding and development locally, at least one significant event with the development of the Blothersburn sequence, which is lacustrine. Palynology from this sequence, according to people like John Marshall, and I've no reason to doubt it, suggests that these rocks are Iphelian to perhaps lower Juvetian. Although there's some dispute about this that I'll come back to in a little while. But again, just to emphasize that this is really important because that marker, that Blobbersburn Formation, is the one that's then correlated right across through the rest of Shetland, through Orkney and down into Caithness. It's the thing that everything hangs on. Okay, we're saying that this is equivalent to the Acheneras and Melby fish beds and so on in other areas. Out to the west, you have the deposits that were laid down in the Clare Basin that are associated with the Clare Field. The correlations here are a little bit less certain, but it appears that Foula is broadly equivalent to the Lower Clare group, although we don't see any fish beds out here because it's in a separate basin entirely. But, you know, I think it's true to say that the Foula sandstones are probably broadly equivalent to the lower part of the Clare group. They're certainly similar in terms of their sedimentology. There's really nice sedimentological information preserved within these sequences where you can actually get at the rocks and walk around on them. This allows you to produce these beautiful sedimentary logs. This is actually one of Graham Blackbourne's logs. It's absolutely fantastic from the Down S formation. Really nice sedimentary structures. We've got sedimentary ripples here. We've got a whole load of soft sediment deformation features here, convolute bedding, Neptunian dikes, some sort of either dewatering cracks or something like that developed on the base of this bed here. And that sediment deformation is particularly prevalent in the lower part of the sequences. And from all of this sedimentology, you can get a whole load of paleocurrent data. This is the paleocurrent data taken from different parts of the stratigraphy. I'm not going to go into it in an enormous amount of detail, but what they show you is a way in which the paleocurrents have changed as the basin progressively filled. In terms of the structures that we see affecting the Devonian rocks, well, the most important one is this big south-southwest plunging synform, which, syncline, but you also see smaller scale structures on the flanks of that in the cliffs. There's one of them there, particularly nicely exposed in the cliffs. Previously, because most of the western side of the island is pretty much inaccessible on foot, there was quite a lot of information missing from the, if you like, the western limb of this synform. But Tom's one of the people in our department who championed and pioneered use of drones to collect multiple low-level aerial images, and from that to build virtual outcrop models from which you can then go about measuring bedding in a virtual way, which allows you to get a much more complete picture of the structure and shows very clearly from the patterns of folding in the bedding, but also in the underlying metamorphic basement, the presence of this south-southwest plunging synform. But the other thing that Tom did, which is really, really neat, was he produced a down plunge projection. That's to say, he removed the plunge of the fold and looked at how the fold geometry changed as you go up through the sequence. These lines here, okay, which are basically a view looking to the south, show the top of the Dunnes Formation, the Soberley Formation, the Snurg Formation, and the Dahl Formation. And the main thing to take out from this, or two things actually, one is that the interlimb angle progressively, well, for the most part, progressively increases as you go up through the sequence. So it's 129 degrees in the lowest part of the sequence. It's 168 degrees by the time you get to the top. So what that's telling us is that as we go up, the folds are opening up. And at the same time, the thicknesses change from one limb to the other. You can see particularly for the top of the Soberley Formation to the top of the Snurg Formation, there's a huge amount of thickening on the western limb. And those changes in thickness are also seen across the Foula Fault. Specifically, for the Soberley Formation, in the hanging wall of the Soberley Fault, you sequences the Soberley Formation, in the hanging wall of the Foula Fault, the Soberley Formation is 400 meters thick. The footwall is 35 meters thick. Snurg Formation, it's a similar change in thickness. And what this is telling us is that we've got a basin development that's very dynamic. We have initially just a simple basement unconformity and some local rivers covering over that metamorphic basement across an unconformity. But then very soon after that, we see evidence that the Foula Fault began to develop, began to control sedimentation, meaning that the Soberley Formation is much thinner on its footwall side than on its footwall side, and then on its hanging wall side. Tectonics stops during the development of the lacustrine deposits of the Blobbersberg Formation, and then we get going again with our faulting, but not only involving normal faulting, now involving sinistral displacements as well, folding of the lower part of the sequence, and the folding continues as the upper part of the sequence continues to develop. And that's why the folds are tighter at the base of the sequence than they are at the top of the sequence. And that's also why, as you go into the later stages of the evolution of the basin, we see that axial flow paleocurrents that run along the axis of the synform become predominant. And that's because the synform is forming in an actively developing basin. In terms of the faults and fractures that we see cutting the Devonian sequences, they're dominated by north-south normal faults, some of which are very spectacularly exposed. Adjacent to those faults, you see beautiful development of deformation bands, which increase in proximity as you get closer to the large structure. You can see the sort of damage that's affecting the Devonian strata here as you get close to the big faults. The faults often occur in fracture corridors, and in many cases, there are many different sets of fractures developed in variety of orientation. And we refer to this as polymodal faulting. And it's an important observation because polymodal faulting, polymodal patterns like this, are indicative of deformation that involves three-dimensional strains, transtension or transpression. And that's backed up by the fact that where you see exposed fault planes, they often have oblique silicon lines associated with them. There's very little mineralization associated with these fractures, surprisingly enough, but just an observation. Now, we weren't able to measure an enormous number of silicon lines in the faults, but we got just about enough to perform what's called a stress inversion analysis. This is where you basically invert the deformation from the silicon lines, and it gives you the orientation of the paleostresses. Specifically, it tells us that in this case, the main shortening direction, or the direction of tectonic thinning, if you like, is more or less subvertical, and the direction of extension is northeast-southwest. But what's also interesting is that there is a small component of compression going northwest-southeast, and that is consistent with the development of the synformal fold, and it's also consistent with the coexistence of this extension direction and sinistral shear along the Foula fault. It is a sinistral transtensional deformation. But how does that work? How do you get growth faulting, growth folding, that's to say faulting and folding that's synchronous with the opening of the basin, and subsidence and filling of the basin at the same time? Isn't that a bit odd? Well, actually, no, it isn't. It's actually very much part and parcel of what happens during a transtensional deformation. Now, transtension is a strange beast. What a transtension is, it's an oblique extension. That's to say that it involves thinning of the crust, okay, to produce accommodation space, but it also involves lateral displacement, in this case in a sinistral sense. And because it involves a strike slip sinistral shear, or a strike slip shear and a pure shear thinning, it produces a deformation that's no longer a plane strain, it's a constriction, in fact. And that involves horizontal extension, given by the red arrows here. And at the same time, you get horizontal compression at 90 degrees to that, and thinning and shortening vertically. So what happens is that as the basin opens up, the material pouring into it can be folded and can undergo folding, so that the lower parts of the basin fill are quite tightly folded, whilst those parts of the basin fill that have only just arrived are only just starting to fold. And so you get this upward opening of the fold structures, okay? The so-called growth folding. These sorts of folds, by the way, you can produce, this is some slightly ancient now experimental work, where essentially they took a rubber sheet covered in clay and stretched it obliquely. And if you do that, you actually produce folds at the same time as stretching and opening up this area. So, and you can do this if you try this with a blanket on a table. Just try putting lying a blanket on the top of a table and begin to try pulling it obliquely apart. Okay, and you will see that you start to generate fold structures just like this. So the point is that you can get folding, synchronous with sedimentation, synchronous with subsidence, so that the older parts of the accommodation space fill get deformed, okay, and influence the paleocurrents that in fact are filling up the younger part of the basin, those so-called axial flows I was referring to before, as summarized in that model. I'm not going to go through that again. Now, this sort of slightly wacky sounding idea of having folding during basin development is actually very widely recognized and has been recognized since 1992, when there was a very famous paper written by a guy called Michel Serran, who did some of the work that he presented in there on Shetland, okay, particularly on the Wallis Peninsula, but also here in Southeast Shetland, and we see similar things up in other parts of Shetland. And it's very nicely displayed at Rover Head here, just north of Lerwick. And here you see that same pattern. You can see this, the sedimentary strata are folded and faulted, and that folding and faulting occurred synchronous with the development of the basins itself. It's not just found in Shetland, it occurs in Western Norway, and guess what, folks? It also occurs in mainland Scotland. This is one example, but there are others just taken here from north of Helmsdale, okay, where we have the Scaraban syncline and the Ousdale syncline developed in Devonian strata. They show the same growth folding patterns, the same sort of northeast, southwest trend. Okay, it's exactly the same pattern. So this sort of phenomenon is actually very common and very often has been misidentified as other things. So to summarize things so far, let's just say three main things. The Devonian strata and the basement of Foula preserve evidence for growth folding and growth faulting. What I mean by that is they preserve evidence for faulting and folding synchronous with the opening of the evolving basin in that part of the world. Plausibly, I put it to you, that's related to regional scale sinistral transtension due to sinistral shear along the Great Glen Walls boundary fault system, probably extending upwards into Norway along the Møre-Trøndelag fault zone system further to the northeast, so that there is a clear geological and tectonic link between these two areas during the Devonian, and Foula demonstrates that very, very clearly. And more broadly, this then is related to the transtensional collapse of the Caledonian orogenic belt and the continuing displacement of the northern part of Scotland and Shetland down towards the rest of the UK. But to finish, I want to ask the question, can we shed more light on the age of the Foula sandstone group and ask what was the Devonian basin configuration? And in order to address that, we can look at some other features, heavy mineral data and detrital zircon geochronology, which are ways of fingerprinting the Devonian sediments that occur in the area. Now, this is not my field, okay? So I'm going to present this in a very superficial way. But all I'll say is that the first technique, which is looking at heavy mineral provenance, basically what this is postulated is you take the Devonian rocks, you crush them up, and you separate out the heavy minerals that they contain. Those heavy minerals are detrital and have been derived from other rocks. And the heavy minerals that you find in different parts of the Devonian sequence are indicative of what the source region compositions were at the time when the sediments were laid down. And you can look at ratios of some of the key heavy minerals like rutile, garnet, zircon. And what these data show, without going into any great detail here, is that the Foula and Melby sandstones overlap best with the late Devonian of Orkney, the rocks that occur on Hoy, and the Lower Clare group. Okay, and that suggests that the Foula rocks were derived from a similar source in terms of composition to the Devonian sequences in Hoy and the Lower Clare group. But perhaps a more powerful fingerprinting method is the detrital zircon geochronology. This looks at the ages of the detrital zircons that you find within your sediments. And here is the data that's in Utley et al., which is taken from the various parts of the Foula stratigraphy and also some data from the Melby sandstone in Melby. And what these are doing is they're fingerprinting the source material ages. But the perennial problem you always face is, well, is that the original age of the source, or has it been recycled several times? And that's always something of an unknown. But what it shows is that for Foula and Melby, we can recognize three or four main peaks. There's a very strong Neo-Archean peak okay, which is no big surprise. We've got a whole load of Neo-Archean rocks just off to the northwest of Foula and Shetland, underlying the Faroe-Shetland Basin, so that fits. We've then got some Proterozoic zircons, possibly two groups, earlier Proterozoic set and a later Proterozoic set, highlighted there in the blue. And then the final peak is Phanerozoic zircons, which are mostly greater than 370 million years old. They represent, or they're plausibly from local sources of various sorts that lie to the east of Foula. One slight puzzle here is that there are no nearby basement sources of Proterozoic age, or of these ranges of Proterozoic ages. So that suggests that these zircons, wherever they come from, they've either derived from somewhere further away or there's some sort of recycling going on here. I'm not going to go into any great detail about this, but a small number of the zircons that we looked at actually give ages that are younger than Iphelian. Remember, Iphelian was the age that the palynology suggested, or was suggested from the palynology, the pollen sequences that are found within the Blobbersburn Formation. So there's a little bit of a problem there, but there are only a small number of grains involved and their significance is unclear. Further work is needed. It could be that those grains have just suffered some sort of post-depositional lead loss. But it does question the rigid assessment of assignment rather of an Iphelian age only to Foula and Melby. They could be a bit younger. But the other thing is that if we compare our Foula data sets with our four main peaks here to the published work from other areas, okay, we see similar sorts of things. So in other parts of the Devonian, particularly the Clare group, Shetland and Orkney, we see similar things. We also see detrital zircons of Neo-Archean and Proterozoic ages within the East Mainland succession, which is a basement succession in Eastern Shetland. And then Eddie Dempsey and Anna Bird did some fancy multi-dimensional scaling plots, which I really don't understand. But what they show is that the Foula and Melby sandstones, their zircons, are very much intermediate in terms of provenance between those that we see in the Clare group and those that we see in Orkney. Now that is quite significant because if we then try to reconstruct the Devonian Basin as it was at that time, okay, so what we've done here is we've restored, okay, Fair Isle adjacent to Wiles, okay, so we've restored the dextral displacement along the Wiles boundary fault. We've added in some other, or removed, should I say, some other postulated dextral displacements along the Melby fault and other structures. And that puts Foula here right in the middle of the basin, okay, significantly south of the rest of Shetland. Okay, sorry, Foula and Melby, significantly south of the rest of Shetland. And you can see that it sits geographically about halfway between the Clare field and the Clare Basin, which is up here, and Orkney, which is down here. So that fingerprinting that we saw from the heavy mineral data and from the detrital zircons seems to fit rather well and suggests that Foula is right in the middle of this complex basin system. A complex basin system formed due to, sorry, didn't show that before, formed due to sinistral strike-slip displacements along these major subvertical strike-slip faults and combined with essentially northeast, west-southwest extension due to regional sinistral transtension and collapse of the orogenic belt. And so Foula is just a very small place, but it occupies an absolutely central position in this complex basin system. And it's the only fragment that we have left. So to conclude, Foula, I think, is a small place with a lot to tell. It preserves a 1.6 kilometre thick sequence of Middle Devonian sandstones, which are spectacularly exposed in kilometre-long cliff sections. Those Devonian rocks unconformably overlie probable Precambrian age Yell Sound group, I would suggest, amphibolite facies basement rocks, intruded by sheeted granites. We've done some new drone mapping of the cliff sections, and that's allowed a much more complete structural analysis, which, together with the observed changes in stratigraphic thickness across the island, show that both faulting and large-scale open northeast-southwest folding were contemporaneous with basin filling, what I've called growth faulting and growth folding. That, I suggest to you, is consistent with models invoking regional sinistral transtension associated with movement along the Great Walls boundary, Great Glen Fault System. And the detrital mineral evidence suggests that the Devonian sequences of Foula and Melby are intermediate in character between the Clare Group and the Orkney successions, which lie respectively to the north and to the south. So Foula is very much the centerpiece of this part of the Orcadian Basin. And that, together with the structures that it preserves, is why Foula is important. I'm sorry, I'm getting very, very croaky, Bale. I'm going to stop the sharing, turn my screen back on. Oh, there we go. And that's me done.
Very good.